of last year. So almost everything I will tell you, you can find in more detail and then more carefully laid out in this paper. So the story will be the following. So what I will try to connect some unknown new physics, that we don't know where it is and what it is, through a series of effective theories down to low energy effective theory. That is something that is known to everyone as a Liang Lagrangian, something that describes nuclear beta transitions, and then by constraining the parameters in the Liang Lagrangians from the all available measurements, I will try to learn something more, go back and learn something about the new physics at very high energies. That's a very rough sketch, in this for what I'm trying to achieve. And what I have to start first is exactly with this language for nuclear beta transitions, but not in a maybe old textbook sense, but more from the point of view of effective field theory, some more modern description of the fundamentals of nuclear beta transition. So nuclear beta transitions, they probe how first generation quarks and lepton interact with each other. Because the process here is neutron goes to proton and electron neutrino, but in an even more fundamental way, we have a up quark going into down quark, or down quark going into up quark, and then emitting electron and neutrino. So this is what we'll be probing, and the most efficient description of that will be in the language of effective field theories. And to understand, how do we go from this some new physics at very high energies, to effective Lagrangian describing nuclear physics. Let me just guide you through this series of effective field theories. So in the standard model, this interaction between the quarks and the leptons that underlies the beta transitions is mediated by the W boson. So this we know this exists. We know we have this process at high energies, but we could have some other processes. We could have like for example a heavier copy of a W boson that I call W prime, or we can have a leptoquark. This is how leptoquarks look like. And they also could lead to this kind of transition between the quarks and leptons. And finally, we could have our W boson can mix with the right-handed W boson and lead to the diagrams like that. So there's many possibilities how this interaction could happen at very high energies. So let me so how do we describe it in a model-independent language? And the model-independent language is the language of effective field theory. So if we go down, so we make an assumption here that new physics is heavier, that it's heavier than the electroweak scale, with maybe it's 10 TeV, maybe it's more than that. But then we go down to energies of 100 GeV, so and then the available particles at this energy will be those of the standard model. So what happened to these interactions, to these effects of the heavy particles? They are not gone. They don't vanish. They are just they will be encoded in the new contact interactions between quark and leptons that were not present in the standard model, and also they can be encoded in the in the modified interactions of the W boson with leptons and with quarks. And in the language of effective field theories, this can be summarized in some number of effective operators, of the effective dimension 6 operators that we add to the standard model. For example, these operators that I marked or circled in blue, they are 4 fermion operators. They are 4 fermion dimension 6 operators that we can add to the standard model, and they contain 2 quarks and 2 leptons, and they all lead to some version of this interaction, but maybe with different tensor structures, depending on which operator is present here. And these operators that I encircled in red, they will lead to, after electroweak symmetry breaking, when Higgs boson gets a VEF, this will give you new kind of interaction between the W boson and quarks and W boson and leptons. For example, you can even have interaction between the W boson and right-handed quarks, which are not present in the standard model. And in the case where right-handed neutrino exists, you can also have this kind of interaction between the right-handed neutrinos and the W boson, and so on. So there is all these different possibilities, yeah, are encoded in this different dimension 6 operators. But this is so we could make a dictionary, yeah, between them. For example, if we have a W prime, then this W prime will generate this kind of 4 fermion operator, yeah, that connects the quark doublets and lepton doublets, yeah, because the W prime by assumption will couple just like W, yeah, to SU2 doublets. But on the other hand, if we have a leptoquark, that this is we can generate a different kind of effective interaction at the electroweak scale. For example, we can generate this kind of interaction with a tensor structure or with a scalar structure. So, and finally, if we have a mixing between the W and the W left and W right, yeah, we will generate, as I said, this operator that gives us the W coupling to right-handed quarks after electroweak symmetry breaking, and so on and so on. Yeah, so all these different possibilities.
So
yeah,
Adam, there's one quick question, I think, by Anupam, who was asking why no Z to lepton plus lepton minus effective interaction.
In a sense, why there is no Z boson here, or in this?
Z boson lepton plus lepton minus effective interaction.
Yes, so I would be interested only in these nuclear beta transitions, which are always proceed by charged currents. Yeah, so that's why I'm focusing on the W boson and yeah, on the charged.
Okay.
So, but that is what is happening at the electroweak scale, but that's not what you're interested in really, because nuclear beta transitions, they happen at very low energies. Yeah, at the very at energies below electroweak scale, it's not economical to use the whole standard to have all the standard model degrees of freedom propagating. We should integrate out the heavy degrees of freedom in the standard model, which in this case are the W boson, top quark, Higgs boson, and get a different effective theory that where we only have the light degrees of freedom, just like the quarks and leptons. So in this case, this is not only correct, yeah, from this effective field theory approach, that in a sense that the calculation of loop corrections will be but I mean the perturbative expansion is better defined, but it's also much simpler in the sense that large number of different operators at higher dimensions then simplifies to a smaller number of effective interactions that are relevant for this process of nuclear beta transitions. And in this case, we can single out at the leading order in this effective theory expansion, we can single out 10 different operators, yeah, that are relevant here. And these are all 4 fermion operators with electron, neutrino, up quark and down quark. And then again, different tensor structures. Yeah. On the left-hand side, we have an interaction of left-handed neutrino, but we can also allow for the possibility of having a right-handed neutrino, and then we can, we can have these interactions also on the right-hand side. So all in all, we have 10 different interactions with 10 different parameters, and the goal will be to somehow measure these parameters in experiment. If the standard model is true, then we know the answer. Yeah, then we know the answer that there will be only this V minus A interactions at the energies below the electroweak scale. Let me remind you that W boson is no longer here, so there is all the only effect of the W boson, yeah, is this kind of contact interactions. But if new physics is there, if there is some new particles, leptoquarks or W primes or such, then we can have any of these new interactions, yeah, in addition, yeah, to the ones in the standard model. So now we know what we are after. Yeah, we are after these 10 parameters in the effective Lagrangian at energies below the electroweak scale. And again, we can write down the dictionary. Yeah? For example, if we focus on this version of the theory called SMEFT, where there are only left-handed neutrinos, yeah, at the electroweak scale, and then we don't have right-handed neutrinos, yeah, then we can write the mapping, yeah, between these 5 remaining parameters and the operators in SMEFT, and this mapping, yeah, will look like something like that. Yeah. So there is, again, we'll have a dictionary when we at each step, when we go into one effective theory from a more fundamental effective theory to a less fundamental effective theories at lower energies. Yeah, we have this dictionary, and we can relate the parameters between the effective theories. So this is the effective Lagrangian we will work with, but again, this is not what we want, because something happens. Because again, we have to go to even lower energies to describe nuclear beta transitions, and something happens at this energies of order 1 to GeV, that we have this phase transition, that the correct degrees of freedom are no longer quarks but hadrons. And in this case, what we are the relevant hadrons will be proton and neutrons, yeah, the nucleons. We are not interested in all this hadronic zoo, fortunately. All we need to describe beta transitions is the protons and neutrons. So the effective theory that we have to write down is not in terms of quarks, but in terms of these nucleons, and it's almost exact copy of what I had in the previous slide for the quarks, yeah. But now instead of the quarks degrees of freedom, we have a proton and neutron degrees of freedom, and this is the effective Lagrangian that will be relevant for to describe the decays of, for example, of neutron into proton and electron and neutrino, but also the whole whole host of other beta transitions in heavier nuclei. And this Lagrangian, this is nothing new. So this is something that was already written down by Li and Yang in the 1956. This already during those days, yeah, they were thinking in this. They were in this effective theory mindset. Yeah, this is quite spectacular. And the reason why they were in this effective theory mindset is that because they didn't know what is the true the correct interaction between the nucleons and leptons. So they wrote all possible ones consistent with the Lorentz symmetry, and then they found that there was 10 of them, 5 with left-handed neutrinos and 5 with right-handed neutrinos. So these are colored parameters. Yeah, they will be called Wilson coefficients. Yeah, they are dimensional parameters that we are interested to determine. Now we can make the mapping between the quark level Lagrangian and the nucleon level Lagrangian, and the mapping is here. For example, Adam, yes, please.
Right, Adam, I have a question. Sorry, just clarification. So could you go back to your last transparencies?
Yes,
so please. It's related to something like that. So when you are still talking about order GeV show lower observables, somewhere the two things that needs to be manifest, right? One is the chiral symmetry, not chiral, the isospin symmetry itself, which comes out of the chiral Lagrangian framework, where you, I mean, in the framework itself, you basically replace proton by a non-relativistic degree of freedom as well. So two things is that when you are writing an operator like that, are you using the non-relativistic framework for the baryons?
That will be actually one more slide later for the relativistic fermion. But about chiral symmetry, so chiral symmetry doesn't enter when I write down this Lagrangian, but the chiral symmetry enters when I do the mapping. This mapping is based on the input from chiral symmetry. Yes, for example, chiral symmetry tells you that this parameter GV here is equal to 1 up to small corrections, yeah, that are actually second order in this. Yeah, so this is what you can learn from chiral symmetry and the related current conservation. Yeah, but if you working on with this Lagrangian, chiral symmetry doesn't enter here, yeah, as a building principle.
Meaning that the isospin is part of the chiral piece, right? So the isospin violating effects, and it's, I mean, if you want to include isospin violating effects in the observables of protons and nucleons, right?
Mm-hmm.
So in that framework, you do have the spurions that corresponds to isospin violation, that how it flows into the baryon Lagrangian as well, no?
So okay, so again, so when I write the Lagrangian, so I don't use isospin because isospin would connect the protons and neutrons, or so some different kind of currents. But again, when I will be computing observables, when I compute the matrix elements, for the nuclear beta decays, again the isospin, so or the chiral symmetry, is the very important ingredient in the calculation of this matrix element. Maybe I will tell you a few words about it later. Yeah. So Lagrangian is completely general, and but the chiral symmetry plays a role. So again, we can write down this map, between the parameters. So they are like almost one-to-one. So we have a tensor, for example, tensor current, going into this tensor parameters. Sorry, and then there is a scalar to scalar and so on. It's a little bit more complicated, for the vector and axial current. And one thing that you learn from this mapping is that in the limit where we recover the standard model, where we put all the epsilon to 0, then there is two Wilson coefficients in this effective Lagrangian that are non-zero. These are called the CV plus and CA plus, and this corresponds to vector and axial type interactions in the low energy effective theory. So we have a few non-perturbative inputs that we have to include now in this mapping, because so as I was already saying, by using the chiral symmetry arguments, we can say that this constant that is relating the vector Wilson coefficients to the quark level parameters is equal to 1 to a very good approximation. But for example, for this parameter, which is called the axial coupling, is not there is chiral symmetry or isospin symmetry doesn't fix this parameter. This is something that we have to get from the lattice, and the lattice already gives us 1% level determination of this parameter. So when we want to relate this two, we have to use the lattice input. And similar for the scalar tensor and pseudoscalar currents, we have a order 1% info from the lattice, or up to plus some also theoretical input. So this level of precision is in most cases quite satisfactory. There is also one more thing that has to be taken into account when you do precision measurement. These are this so-called short distance or inner radiative corrections parameters, which are denoted here delta RV and delta RA. And this is actually there is some story about it, because this is a difficult calculation that also it's a loop calculation that also involves non-perturbative inputs, some dispersion relations, and so on. And there has been some controversy about what is this value of these parameters. There is quite a recent calculation that made that gives you the most the best determination of this quantity here that is enters in this matching. And this has a smaller error than the previous calculation, but was also like almost 2 sigma, more than 2 sigma away from the previous calculation. So there was some controversy, and it's slowly getting now it's slowly getting this controversy is getting clarified. Another thing is that, for example, this loop corrections can be different for vector and axial interactions. And funny enough, this difference between the two, so it was known for a long time that they should be more or less equal, but the difference between the two was calculated very recently for the first time in this paper. Just as we were finishing our analysis, then we had to again redo all the codes and put this new input here, because it was actually important and it was changing the result in an appreciable way. Okay, so pertaining to the last question, so one should actually go even further down this rabbit hole of effective field theories, because nuclear beta transitions, they happen in a non-relativistic regime. The mass difference between the neutron and proton is much smaller than the mass of the neutron and proton. So the nucleon fields are behaving in a non-relativistic way, and you can actually simplify the description by going from the relativistic Lagrangian to the non-relativistic ones. This can be done basically by a change of variables. Yeah, you go from a nucleon field to a non-relativistic nucleon field, and rewrite this Lagrangian in terms of the non-relativistic nucleon field. And then it gives you actually that very interesting simplification. One thing that you can learn from this exercise when you go from relativistic to non-relativistic is that at leading order, the pseudoscalar interaction drops out. So when you, in the leading order, when you look at nuclear beta transitions, you will not have a sensitivity to pseudoscalar interactions, but instead you could have a sensitivity to all other interactions, CV, CA, CS, and CT. Another thing that you can learn is that there is only two matrix elements, yeah, that you need to calculate nuclear physics transition. These are, you have to be able to, when you now go from this non-relativistic Lagrangian to observables, yeah, you have to calculate the matrix element of this nucleon fields between nucleus states. And there is only two, in the non-relativistic case, there is only two structures that appear, and they correspond to the two types of nuclear transition. They are called Fermi transition and Gamow-Teller transition. If this matrix element is non-zero, then the transition is called the Fermi transition. If this matrix element is non-zero, then it's called Gamow-Teller transition. And if both of them are non-zero, then it's called mixed Fermi Gamow-Teller transition. So this language of nuclear physics that maybe you heard in some graduate courses, yeah, in a completely different way, is actually follows from effective theory, from the relativistic version of the EFT for the nucleons. And that at leading order, you just have two different operators that lead to these two different transitions. If you go beyond the leading order, then you will have operators also with derivatives, and they correspond to so-called forbidden beta transitions. But I'm not going to talk about forbidden beta transitions at all in this talk. So I will talk only about so-called allowed beta transitions that are mediated by one of these two matrix elements. Okay, so this is the summary of the language. Yeah, so we will have this effective Lagrangian, the linear Lagrangian, except that we know that we can get rid of the pseudoscalar couplings because they will not affect our observables at the leading order. And the goal is now to determine all of this, all of this couplings from the available data. So we have this 8 Wilson coefficients that we want to measure and given the available information. So now I will and then we
wait. What happened to the form factors?
They will be there in the observables, of course, yeah. But yeah, okay. I said that at the fundamental level, we have 8 parameters.
Got it.
Fundamental parameters that we want to determine. When we go to observables, yeah, we need also this matrix element. So they are not really form factors because the Q-squared dependence, yeah, there's very little Q-squared window here, so they are more numbers than form factors. But yeah, we'll be needing them, and I will mention, yeah, how we actually get around that, yeah, in this business. So let me now move to the next topic. Yeah, so now I discussed the language. Yeah, so we know what we want. We are after these 8 fundamental parameters of fundamental 8 Lagrangian parameters in the Lie Lagrangian, and we want to relate them to some observables. Yeah. So what are the observables in the allowed beta transitions? So allowed beta transition, yeah, so we have this kind of picture. Yeah, we have a nucleus with some spin maybe and some isospin quantum numbers. It's moving, turning into another nucleus with different isospin quantum numbers and into electron and the neutrino. So this is the cartoon, yeah, of what's happening. So the first thing we can calculate, yeah, for the transition is the total width. So that's the most obvious. So the total width, or which is related then to the lifetime. So what will be the structure of this calculation of the result? So this total width, yeah, will depend. Yeah. So this is just
a question here.
Yes, please.
As far as I can see, the description that you have presented is the same as what was used in the 50s.
Yes.
There's no change in the description.
No.
So
yeah.
The new thing will be the experiments that you can.
Yes, of course.
Okay, thanks.
Yeah. So I mean, what is different in the 50s? Yeah, is maybe this instead of that we have starting with the EFT Lagrangian, we actually embed this Liang Lagrangian into the whole ladder of effective Lagrangian that go from by a weak effective theory to the SMEFT to new physics. Yeah. So that there is a difference of perspective, but the formalism, yeah, was there before. Yeah, of course.
Would it be okay to say that because you are at every level, you are using tree-level matching to the, in the effective Lagrangian, and as a result of which you are basically not seeing any difference from if you have naively written down, just take into account dimensional, all the operators take into account the non-relativistic dimensional counting.
So it's not completely true, yeah, that we are, so this, when we do the matching, yeah, this parameters, so this component in the matching comes from the loop level, yeah. But yeah, so there is a loop component, yeah, when you connect to your effective theory, yeah, to more fundamental description, yeah, in terms of.
But that you are getting from the lattice calculations, right? So that's like you take the formalism operators and calculate it from lattice
dispersion relation, yeah.
That.
But yeah, this is somebody else calculated it, yeah, and I'm using this result here. Okay, so now
one more thing. So when you are matching the EFT in the non-relativistic regime, your argument was that the corrections to the leading order matching, basically you are taken, the correction from that is small, which is also related to why these nuclear form factors, the Q-square dependent pieces are also small, right? Yeah. So these were suppressed by the proton masses scale, roughly. Is that the suppression?
So the expansion, yeah, is here the momentum exchange, yeah, which is MEB, yeah, over the squared over the
proton mass squared, and that's where your suppression is a lot more enhanced than the usual. Okay.
Yeah. So because this is a tiny parameter below the current sensitivity of this transition. So.
Surinder?
I'm sorry to interrupt, but I had one more question here. So if you wanted to go beyond old technology, for example, you would take higher dimension operators. Okay. At the nuclear level, you do not really have any other long distance fields to work with, except the ones that you have already put in.
No.
So the only change would be if you had two nucleon currents and one lepton current, or one nucleon current, two lepton currents, right?
Right. Yeah, but so I haven't looked. So how could we have one nucleon current, two lepton currents? Yeah, this doesn't fit in this. But we could have the same currents, like I've written here, but with a larger number of derivatives. Yeah. And this would also contribute, yeah, to the allowed transitions. But again, this effects will be suppressed by additional powers of Q squared over the nucleon mass squared. Yeah, and this will not.
I wonder though. I mean, the derivatives would have to couple to a vector field, and there's no vector field present, right?
No, there's no vector field present.
So what could possibly change this?
So
as I said, there could be a Q squared piece, no? It's simply Q square.
Yeah. So for example, there could be two derivative corrections. So if we have this effective Lagrangian, yeah, when we go beyond this leading order in the derivative, so this is a special derivative now, non-relativistic expansion, special derivative of the nucleon mass. So when we get to the second order, and this, yeah, there will be again.
Yeah, so that's it. Yeah, right. Absolutely, that's it. So these charges just convert into form factors. That's it. in the old language. These charges become Q-square dependent.
Yeah, exactly right. And that's how we do the form factor in Chiral as well. No? It's the same, I think.
Could you have a contraction with nu bar sigma k L with gradient k though?
Yes. But this would give you something that would contribute to so-called forbidden beta transitions, because it would change parity of the nucleus.
Okay, I see.
So this is something interesting. This is something actually I'm thinking about now. Yeah, but it's not in the. Yeah, it will be not. I will not talk about it here. Okay, so yeah, going back to this structure of the results. Yeah, so we'll have dependence on the so-called Fermi matrix element. Yeah, here because and this Fermi matrix element is to first approximation that can actually be calculated from isospin symmetry and is given, it's just some expression given in terms of isospin quantum number. So if you know the isospin of the nucleus, you can calculate this MF in the first approximation. Then, of course, there is isospin breaking effects. And if you go to the per mil level precision, you have to take them into account. And these isospin breaking effects are difficult, and they have to be calculated at this moment from some nuclear models. Yeah, but this isospin breaking effect would be, for example, part of this higher order corrections. There will be also some electromagnetic corrections and so on. Then there will be this width will depend on the phase space. This phase space varies very much, yeah, for different decays. Because the mass difference between nuclei is very, very different here for different nuclei. So there is this phase space factor, and then the dependence on the fundamental parameters, on the Lagrangian parameters, will enter to these two combinations here. This is one combination that appears, and the second combination, that's so-called Firth term, that comes with this factor of m over e integrated over, averaged over the phase space. So this is how you get this. So this is the structure of the total width. One thing that I already want to show is that we have this dependence, yeah, of this parameters on the so-called mixing parameter. So the width of the decay will depend on the mixing parameter that depends on the ratio of the contributions of the Fermi and Gamow-Steller matrix elements. And this is an inherently non-perturbative input that is very difficult to calculate from nuclear models, yeah, and we'll have to get it from experiment eventually. So I will come back to this. So you have this combinations of things that you can calculate or you can estimate by symmetry arguments, and dependence on this fundamental parameters. Now, there is something about the language that nuclear physicists use. Yeah, that instead of the lifetime, first they will use half-life. So that's just a quirk. Yeah, you have to multiply the 1 over gamma by the lifetime by logarithm of 2. But you see that if you take a half-life, it will be very different for different nuclei. So nuclear physicists like to use the quantity that they call Ft, which is T, which is the half-life multiplied by this phase space factor. So they just factor out the phase space factor from the result, and this is called, instead of a lifetime or half-life, this is called Ft. And finally, there's even more one more simplification that they do in presentation of the result. This parameter, this higher order corrections delta that come from isospin breaking or from radiative effects, they are also very much dependent on the transitions. They are different for different transitions. So they also factor it out from this result. So this is something you calculate, and then you factor it out, and then you get something with the big Ft observable, which is lifetime, yeah, with all these things that are dependent on the transitions are factored out. So all in all, the transition dependence enters either via this x variable that I defined here, yeah, that depends on all these different Lagrangian parameters, and also depending on the mixing parameters, and via this Firth term, yeah, where this for example, this factor m over e averaged over the phase space, yeah, is depends on the different transitions. But this is not all that is measured in the nuclear beta transitions. We also have so-called correlations. So instead, so correlations is basically angular observables. And the simplest correlation we can look at is the so-called A parameter, which is the correlation between the in the angle, relative angle between the electron and the neutrino. So how do you know where the neutrino went? Of course, you don't know where the neutrino went because in this experiment you never detect neutrino, but you know where you can detect the recall nucleus, and then you by conservation of momentum, you can reconstruct the momentum of the neutrino. So you can plot the differential distributions in this relative angle between the electron and the neutrino, and this coefficient here is called the little a parameter. But there is more information you can also extract if you have if you have a magnetic field and you can polarize the nuclei. Then you get another vector that you can use to define the correlation, which is the vector, the spin vector, the direction between the nuclei are pointing. And then these correlations between the electron direction and the spin direction and the neutrino direction, the spin direction, are called big A correlations and big B correlations. And this is also measured in nuclear physics experiment. So the important thing is that if you now express this correlations like A, little a, and big A by the fundamental parameters, they will have a different dependence on this Lagrangian parameters than lifetime, for example. So if you measure these different correlations, yeah, you measure different combinations of the parameters in the Lagrangian, and once you measure enough of these observables, you can actually reconstruct all the parameters in the Lagrangian simultaneously by combining a large number of different observations. So there is so this is the expression, yeah, for this differential distribution for the beta transition, yeah, and there are all these correlations here, A, little a, and by the fifth term B. Then there is a correlation C that no one ever talks about because it's more challenging experimentally. And then there is another correlation D that violates CP. And I will not talk about it. This is again something very interesting. But I will be assuming that my parameters in the Lagrangian are CP conserving, and I will ignore all the CP violating effect in this discussion. So what are the data? Yeah, so what we can use which data we can use to make this analysis, yeah, and combination of the parameters in the Lagrangian. So there is three most important classes of data. The first one is called super allowed 0+ to 0+ beta transitions. I will by abusing a little bit of language, I would be calling them super allowed because I don't want to say 0+ to 0+ every time. But 0+, 0 to 0+ means that both the initial and the final state nucleus, they have a spin 0. And this gives you a very important simplification, because then you can show that for the 0 spin, the gamma of Teller matrix element, because it has this vector structure, it vanishes. So there is no gamma of Teller contribution to the matrix element, and so there is a big simplification because you don't have this unknown parameter, mixing parameter here that is entering, and your result for the FT observable, for this glorified lifetime observable, only depends on this parameters in the Lagrangian, which are the same for every transition. The only thing in this formula that is different, can differ between the different transition, is this M over E, which this average of M over E, which is transition dependent, as is shown in this column. However, yeah, so this is just as good, because then what you expect, if the standard model is true, this B parameter is 0, because it depends on the scalar interactions that are not present in the standard model. So if B is 0, if you have a standard model, then everything else is universal for all beta transitions, and this FT should be the same for all beta transitions. And now, if you look at the compilation of the latest values that have been done for the last 30 years by this by this brave people, Hardy and Towner. They are compiling the available data and determining this FT values for different nuclear beta transitions, yeah, that are of the super allowed type. And they find that indeed they are all, the value that you get from all the beta transitions is very close to each other, which means that they are consistent, the data are very consistent with the standard model. Another thing that you should see is that the precision of this determination of the FT is quite amazing. If you think about nuclear physics as something very dirty and rough, here this is not true, because in this particular case, you have a per mil, better than per mil precision for individual measurements, and you have many different transitions. So all in all, you are reaching the 10 to minus order 10 to minus 4 experimental precision in this case. So because this M over E is different for different nuclei, the fact that you're observing FT that is similar, it means that this new physics contributions from the field term is small, and this will constrain the scalar interactions in the Lian Lagrangians. Yeah? So this fact that they are the same gives us also some information about the structure of new physics. Next thing, we have also a lot of data about neutron, and also with precision that are better than per mil. We have a data about the lifetime of the neutron. For the neutron, customarily one doesn't use FT, but one uses the usual lifetime like we use in particle physics. But there is also measurements of the correlations of A and B and little a, also with precision of the order of 10 to minus 3, 10 to minus 4. So for the lifetime, there is a story that maybe you've heard about, yeah, that there is a different kind of different type of experiments measuring this lifetime. One is called beam, the other is called this bottle. In the bottle experiment, I will be vulgarizing it. Yeah, you put the neutrons in the bottle, and then after some time you check how many of them remain, and then you measure the lifetime. And in the beam experiment, you have some neutron beam, and then you detect the protons there from the decay of these neutrons. And these two types of experiment, they give you a bit different results that are quite discrepant. If you look at closely also the different bottle experiment, these are actually two different methods of confining the neutrons in the bottle, also give you quite different results. So there is a little bit of confusion, but particle data group has a good strategy what to do in such a situation. So if you have a lot of kids in the room and somebody broke a window and you cannot find who did it, yeah, then you just penalize everyone. And particle data group penalizes everyone by just blowing up the errors such that after blowing up the increasing the size of the error bars, you increase them to the point where the data are consistent with each other. And you have to blow up the errors here by the factor of 1.9 to achieve this consistency. And this is also what we will do in our analysis. This problem with the neutron lifetime, yeah, has been known for a long time. Yeah? I mean, this is quite something that people talk about a lot. But until recently, there was another problem with the neutron data, which was with the beta asymmetry. Beta asymmetry, let me remind you, is this coefficient in the distribution between the angle between the electron direction and the direction of the spin of the neutron. And then again, there were older data that were showing a different value than the newer, more precise measurement. And again, for a long time, particle data group was penalizing everyone, and I think they are still penalizing. But actually, if you apply the algorithm, yeah, so you find that actually now you are free to discard this order measurements and only use the newer measurement in the combination. And then you find that actually the larger error, yeah, that was caused by this older measurements and blowing up the error is gone, and then you get a very precise new measurement of this beta asymmetry correlation. So these are the most important data that we are using, and also we are using there is some other measurements of different correlations in different nuclei like helium, argon, and cobalt, and so on. We are putting them into our feed. Also, they actually matter a lot. If we discarded them, the results wouldn't change a lot, but we put basically all per mil level measurement or percent better than percent level measurements that are available in the market. So they are also in our feeds. And then there is something new that was included for the first time in the BSM context only in this this paper of us with Martin Gonzalez Alonso and Oscar Navilliat. And these are so-called mirror decays. Mirror decays are the transitions between isospin half and same spin and positive parity nuclei. So for example, neutron to proton is an example of a mirror decay, but it's not put in the same basket. But you have different examples of similar structure in nuclear beta decays. You have a lot of decays of this type, yeah, where the parent nucleus, yeah, has the same spin as the daughter nucleus. So for example, tritium decay is of the type of carbon 11 or neon 19 and so on. So there is a lot of this so-called mirror decays that are available in the experiment, and they are theoretically tractable, yeah, because there is because of this mirror structure, so that what you get is the same nucleus, but just with the some mirror means here that you just change. If you replace neutrons and protons with each other, then you're getting the same nucleus, yeah, as you started with, yeah. So what happens, for example, yeah, if you have 9 nucleons, 5 neutrons, and 4 protons, you turn it into a nucleus with 4 protons and 5 neutrons, and so on. So this class of mirror decays, yeah, is quite large, and there's been also quite a lot of very precise measurement of the FT values. But here, FT alone doesn't help you, because the problem is that the theoretical expression, yeah, for this lifetime, for this FT lifetime, contains this mixing parameter. Now it's non-zero. Now that the nuclei, they don't, the initial and the final nuclei, they have non-zero spin, and this raw parameter is non-zero, and this means that there is an unknown parameter that enters in this expression of FT. So if you only have the lifetime measurements, then you can only determine from experiment this mixing parameter. This is something that you cannot calculate very precisely from nuclear models, and there is no good idea how to calculate it by different methods. Like lattice is not anywhere close to calculating this kind of observables. So lifetime measurements don't give you enough information to actually measure this fundamental parameters from the Lagrangian. However, there is a subset of mirror transitions where you have information not only about the lifetime, but also about correlation. There's some correlation that is measured precisely. And then you have 2 combinations of the mixing parameter and the Lagrangian parameters that are measured. So you can determine the mixing parameter from one and then put it into the other. Of course, what we do is just to put all the information together. So there is 6 mirror transitions. They're shown here, yeah, fluorium, neon, sodium, and so on, yeah. So this where we have this information. So we collected this information and we put it also in the feed to get better constraints on new physics. So now I come to the results. So what did we get from this exercise? So let me first, to set the stage, let me first tell you about the result in the standard model case. In the standard model case, so we assume that there is no new physics. And then if there is no new physics, then this low energy Lagrangian only contains vector and axial interactions. There is no right-handed neutrinos because I assume the standard model, and there is no tensor and scalar interactions. In that case, if we, in the standard model limit, we can, from all the observables that we use, we can determine CV and CA to a precision, to accuracy of order 10 to minus 4. And this is quite impressive. And because we put mirror decays in the feed, we also at the same time determine the raw parameters in this transitions, also to an accuracy of the level of 10 to minus 3. This so this has no interest for fundamental physics, because this law is, there are some strong interactions parameters. They depend on the nuclear matrix elements, but we yeah, this is some result that then can be compared with to some nuclear models. Yeah, and this is also something that is maybe useful for some cases. However, the measurement of this first measurements of CV plus and CA plus are very important, because they can be translated. If you now take this dictionary, they are mapped into VUD and the axial coupling. Yeah, in the standard model. So VUD is an unknown parameter, fundamental parameter in the standard model. So this is a measurement. This measurement of CV plus is a measurement of VUD, and the measurement of the GA is not a fundamental parameter. It's the axial coupling of the nucleon, but this is a QCD parameter. And you can see that from the experiment, we can determine this parameter with a 10 to minus 4 precision. On the other hand, from the lattice, you can only get percent level precision. So this is something that gives you a cross-check of the lattice calculation of GA. It is much more precise. For the VUD, we extracted VUD, and this is our value. And for this value of VUD, there was also a lot of confusion, which was related to this confusion about calculating these inner radiative corrections. And the previous calculations were from Marciano and Sirlin were giving a larger value of VUD, and then it went down with a little bit smaller error. However, our value has a larger error. Why do we have a larger error? Because there was also some development on the front of calculating the nuclear corrections to this to super allowed transitions in these papers by Seng et al. And by Goldstein, and this actually blows up the errors that you have to assign to this calculations. So if you take this into account, the error becomes larger, and the tension with the measurement with the unitarity. So independent measurement of VUS are inconsistent with measurement of VUD if you assume unitarity, but this tension is now smaller if you take into account the larger uncertainty that was neglected in this previous calculation. So this is our value of VUD, and this is the most up-to-date value at the moment in the literature that takes into account all the latest theoretical developments. So if you look at this VUD, the effect of the mirror transitions that we included on this VUD, this was something that was actually done earlier already in this paper in 2008, but we just updated it. You can see that the precision of the mirror transition is still worse than that of the measurement of VUD in neutron decays and in the super allowed decays. However, the precision is approaching to that. So this mirror decay is already providing a useful cross-check of the determination of VUD from super allowed beta transition and from neutron decays. Okay, so this is what we have to say about the standard model.
Excuse me, Adam.
There's
I just wanted to look at the previous slide.
Yes.
Right. So the error bar that you quote on the right is 25 in the last 2 digits, right?
Yes.
And that means 2 sigma. Is that what?
It's about 2 sigma. I would say no. So this is 1 sigma error bar,
yeah.
And the tension, with the VUS measurement and unitarity is about 2 sigma in this.
Right. Okay. So that's about 2 sigma from unitarity.
Yeah.
And if you go to the next slide now, so the mirror nuclei, sorry, the singlet, the super allowed, that's also in tension with unitarity then?
Yes, so super allowed by itself are in, they dominate the determination of VUD, and they are in tension with unitarity. if you look at the neutron data by itself, it's in less tension with unitarity, and mirror is in no tension with unitarity at all. But because 0 plus to 0 plus have the smallest error, they dominate this, and this problem with unitarity.
And there's no understanding about why this could be slightly wrong.
Yeah, there is understanding. A lot of people criticize this Hardy and Towner determination, that they are relying too much on nuclear models and the errors are underestimated. And it's possible that the errors are underestimated in that determination. And that's why it's so important to provide independent cross-checks of this value of VUD from other inputs, which are the neutron and mirror decays.
Thanks.
Yeah. Of course, I cannot say, because I'm not an expert in nuclear models, so I cannot say if they did anything wrong. I'm taking the result at the face value, but I heard some nuclear physics experts criticizing this, saying that the errors are underestimated. So now let's do the next exercise. So yeah, it's already 1 hour. Can I have 5 more minutes? Yeah, it's okay to.
I think 5 minutes is okay. Yeah.
Good. So if we assume that we don't have right-handed neutrinos, we have 4 parameters that we have to feed to this in this global analysis, and we again can feed them, and then we can translate them into the quark level parameters. And then what we're getting is that we're not only getting the measurement of VUD, but we're also getting measurement of the scalar and tensor currents in the quark level Lagrangian, and the precision of this measurements is of the order of per mil. So let me maybe skip you that, but just show you this maybe more propaganda plot. Yeah, that if we looking at the scalar and tensor interaction, yeah, we are in the best case scenario when we assume that new physics is strongly coupled. We can probe new physics, yeah, at the 100 TeV. If new physics is weakly coupled with a coupling of order 1. We actually probing new physics at a scale of around 10 TeV. Yeah, that leads to appearance of a scalar and tensor interaction in the Lagrangian. The precision for the right-handed coupling in the quark level Lagrangian, so the right-handed currents interaction with right-handed of neutrinos and leptons with right-handed quarks is a little bit weaker, and the reason is that this. To get this constraint, we need an input from the lattice, and lattice has only a % level precision, and that's why we are worse than with per mil level precision for scalar and tensors. Okay, so there's also a funny story about this nuclear lifetime, yeah, but maybe let me skip it. Yeah,
Adam, I have a question regarding the precision.
Yes.
So in order for you to calculate the observables at extremely low energy, you are neglecting many corrections, right? Which, for example, you said that there are effects of Q square over Mn square.
Yeah.
There would also be, for example, the pion exchanges in any of the vertices, right? Which would also give you corrections.
Yeah, but it's so small, yeah. So that is something. There are corrections that I have to worry about, but I don't think that these are the ones that I have to worry about.
Right, but here comes the precision of you are reaching it to the new physics, because that's also, if you put it 10 TeV, bringing it down to, I mean, you're looking at an operator of size of, 10 TeV over 100 GeV, that's a factor of 100. This is the 1% effect you're hunting for. So the observable itself, if it has few percent error which you fail to neglect, and then you say that I'm actually hitting a scale of 10 TeV, that's a little bit of problematic, right?
No, I don't think so. I think that you see here there's no problem. So I have to worry a lot about this smaller effects. Yeah, when I measure the standard model parameters. But here, even if I'm wrong by, let's say, 10%, yeah,
Okay.
10% correction, you mean my constraint on the new physics is wrong by 10%. So I'm telling you that I can probe 100 TeV, but in reality I can only probe 90 TeV. That's not a problem. That's
okay. There's order. Okay. Yeah.
So I need a precision for the standard model parameters that are non-zero in the standard model. Here, I'm completely happy with a 10% precision. Yeah, and this is definitely what I'm having. Yeah, I'm having a bit better than that 10% precision for the constraints.
Yeah. Okay.
Okay, so I will not tell you the story about the bottle, and but that is actually very, very, very interesting. Maybe you can ask me later. Let me just tell you, just flash about the results. We also did the fit to all Wilson coefficients at the same time, and this has never been done before. This is maybe funny historical remark, yeah, that in the 50s, yeah, people were confused about what is the structure of these interactions, and then there was some confusion at the beginning. They thought that these are scalar tensor, but then Feynman came and said that it's V minus A. So and this was resolved. But you see that it was never resolved in a complete EFT sense. Yeah, that nobody ever made a fit with all 8 parameters at the same time and prove that the data is pointing unequivocally to V minus A. And this is what we did for the first time. Of course, we did it 60 years too late to really claim any fame, yeah, but just as a historical anecdote, yeah, we finally showed, yeah, that V minus A is the answer, yeah, for the correct structure of the weak interactions. And when we got the constraints on all of these parameters at the same time, the parameters that multiply the interactions of the right-handed neutrinos, the constraints are much weaker. They're only percent level because they enter quadratically in all the observables. So we have less, they give you less effects, yeah, to less contributions to these observables. And to get these constraints, the mirror data were actually essential. Yeah. So if we got these constraints without mirror data, we would get the constraints that will be a factor of 2 weaker for most of the parameters. Yeah. So this was very, very important. Yeah, to have this mirror data included in this analysis. Okay, and then the last thing. This is the last thing. When we did this fit, there is one funny thing, yeah, that there is a preference for non-zero value of CT minus parameter. CT minus is the one that give you the tensor interaction with right-handed neutrinos. And this is just probably some artifact. This is actually driven by one single measurement, the measurement of a little A correlation in the neutron. And probably there is something wrong with that measurement that is causing this anomaly. Yeah, but this is a 3 sigma anomaly sitting in the data. Nobody, if you want to, if you get bored with other anomalies or they go away, you can always come to our anomaly and do some model building, yeah, to explain away this. But yeah, I don't put a lot of weight into this anomaly. I think it will go away when the new data about the correlation in the neutron will come in the near future. So let me stop at this. So, and the summary is, this is a great, this nuclear beta transition is the great playing ground for physics beyond the standard model. We're getting measurements with the precision of the order of 10 to minus 4 for the standard model parameter like VUD, but we're also getting per mil level constraints on the BSM parameters, like the presence of a scalar and tensor currents in the effective Lagrangian. And we can also constrain the interactions of right-handed neutrinos in a completely model-independent way. Thank you.
Okay, thanks, Adam. So the floor is open. You don't need to raise your hands. Please go ahead and ask your questions. So, yeah. So,
yeah. So since you couldn't say anything about it, it would be interesting to see what you have to say about the mirror, the bottle.
Oh. No, so what I wanted to say here, yeah, is that we have this story, yeah, we have this discrepancy, yeah, between the beam and bottle. And what PDG recently did is that they said, okay, we know that beam is wrong, so let's throw away beam and we only use a bottle, yeah, to actually get the our neutron lifetime. And this is we believe in the bottle. Why we believe in the bottle? Because if you believe in the standard model and you predict that what is the neutron lifetime in the standard model based on other nuclear physics input like super allowed transitions, then you're getting these predictions, which is very well in agreement with the bottle results. So beam must be wrong. However, if you do the same exercise, but not assuming the standard model, if you allow the presence of a scalar and tensor interactions also in the Lagrangian, then the predictions of the neutron lifetime actually is shifted. The error bar is of course larger because you're allowing for more couplings, but the prediction shifts, and then it's actually straight in between, very much in between the bottle and the beam measurements. So if you allow for new physics, actually either beam or bottle could be correct. So if you're totally agnostic, you should not discard yet this beam measurement, because they may actually be pointing to a correct value of the neutron lifetime if there is physics beyond the standard model that is affecting scalar and tensor currents.
But of course, you don't get smaller error bars on those two couplings.
So, so of course, there is the discrepancy between them. I cannot explain them.
No, not that. The results that you showed for the 4 coupling fit, the error bars on the scalar and tensor were consistent with them being 0.
Yes, but
there's nothing changes in that error bar, I suppose.
So the way we obtain this plot, is you remove the neutron lifetime input, from the feed, and then use all the rest of the measurements to predict the neutron lifetime, and then you plot this in the plot. So if I remove the neutron lifetime, then I would slightly relax the constraints on the scalar and tensor, mostly on the tensor currents, and the error will be slightly larger. But yes, that wouldn't change a lot. So you still have a per mil level constraints on this scalar and tensor current, but even per mil level tensor currents are enough to shift the neutron lifetime in a way that it could go from bottle value to bottle preferred value to the beam preferred value.
Thanks.
Adam, just it's not a question. Can I go to the slide with the operators? I just forgot. I wanted to just see one more time. Make me take a snapshot.
This for example.
Yeah, that would work. So this one question, actually, I do have a question now related to this. So when you jointly fit with, let's say, CV, CA, CT, and CS, and things like that, where do you get the form factor for the tensor operator?
For the tensor, So
yes.
So if you go, that's the beauty of non-relativistic EFT. If you where were we here? So look here, So this is how axial comes in, which is already present in the standard model. This is how tensor comes in. Axial and tensor have the same matrix elements, the same form factor, which is the gamma of Teller 1. So if you know this form factor, for some precision, you don't need a new form factor. There is only 2 of them, and there's one for axial and tensor and one for vector and scalar. The only difference between axial and tensor is that the latter connects the left-handed and right-handed neutrino, and the former connects left-handed and left-handed. So left-handed neutrino and left-handed electron. So this will lead to a chiral flip. So if you use the CT, it costs you the factor of ME in the amplitude. But okay. This is not a big suppression, because ME over electron energy is over the 1 in nuclear beta transitions. So the only difference between CT and CA is in this
it's okay.
ME factor, and not in the nuclear form factors. And that's the beauty that you see on in the non-relativistic EFT.
Yeah. Cool.
Just one quick question. So the M over E values that you quoted, they came from nuclear structure calculations. So there was a table where you had.
Let me just quickly find it. Yeah, so this is the calculation, yeah, that we did. This is just an integral you do for the phase space. There is also a Fermi function that I didn't talk about at all, yeah, but there is it is there, and then you calculate this average value of m over e, and you do it with just without any nuclear structure. There is an effect from the nuclear structure from the finite size, but it's quite small. So I would say that the value that I present here, maybe this is a little bit misleading, yeah, because I don't have a precision of percent or per mil to it. This is the value that we use. But again, this is a parameter that multiplies new physics effects. So even if I'm wrong by 10% in this parameter, it means that I will just get a 10% wrong constraint on new physics parameter. So I tell you that it cannot be, it is 10 to minus 3, but in reality, it can be as large as 9 times 10 to minus, sorry, it can be as large as 1.1 times 10 to minus 3. So this is very, very simple calculation without using much nuclear input, except for the Fermi function and some finite size. But yeah, the error probably on that is of the order of a few percent.
Okay, yes. Are there any other questions? So if not, just thank the speaker once again.
Yeah, sorry for the break over time, but
hopefully you can visit sometime.
Thanks a lot, Adam. That was a nice talk. Hopefully I'll see you at some point.